At the beginning of the 20th century, it became apparent that certain experimental observations were not able to be explained by the prevailing classical Newtonian physics of the time. It took the introduction of quantum theory to provide adequate explanations for phenomena such as the photoelectric effect, the Compton effect, blackbody radiation, and atomic emission spectra. In this video, we look specifically at atomic emission spectra as a way of evidencing the fact that the energy of electrons in atoms is quantized. And this is the first step in understanding the nature and structure of electron clouds in atoms. The cornerstone of quantum theory is that energy can only be transferred between systems or objects in discrete amounts. These discrete amounts of energy are called quanta of energy, and that's the plural. A single packet of energy is called a quantum of energy. In classical physics and in our everyday experience, it's thought that any object can attain any arbitrary energy value simply by transferring a sufficient amount of energy. For example, in our everyday experience, we feel that we can add or subtract any arbitrary amount of energy to a system or object. It turns out that this is not the case. The energy that an object can attain is actually restricted to certain allowed energy levels, and the transfer of energy to increase or decrease an object's energy can only occur in discrete quantum steps. In other words, energy is said to be quantized. And we can use the heating of matter to demonstrate this quantization of energy. When we heat the atoms within a solid metal to high enough temperatures, they emit white light. For example, consider the tungsten filament inside a light globe, which is heated by passing an electrical current through it. Such an emission is known as a continuous emission, since white light is actually made up of all the colours of the visible spectrum, and the visible spectrum is only a small part of the overall electromagnetic spectrum. Now, when we heat the atoms of gases rather than solids, we see something quite different compared to the solid state. What we see is the emission of light colours in discrete, non-continuous bands. For example, the emission spectrum of hydrogen atoms in the gaseous state shows visible lines or bands at wavelengths around 656 nanometers in the red part of the visible spectrum, 486 nanometers in the blue-green part of the spectrum, 434 nanometers in the indigo part of the spectrum, and 410 nanometers in the violet part of the spectrum. When we heat helium gas, we see similar discrete non-continuous bands of light emitted, although the number and the positions of these bands is different, and indeed the position and number of bands is characteristic of helium in this case, as was the position and number of bands being characteristic in the case for hydrogen. To understand the implications of this type of line spectrum, we need to know a bit more about light in general, and we need to know that each of these wavelengths corresponds to a particular frequency of light. We can see that as the wavelength of light or electromagnetic radiation increases, the frequency decreases. And wavelength and frequency are inversely proportional according to the relationship lambda equals c on nu, where lambda is the wavelength, c is the speed of light and it's a constant, and nu is the frequency of the oscillation of the electromagnetic wave. It's also important to know that each wavelength or each frequency of light corresponds to a particular energy, described by the Planck-Einstein equation, which shows that the energy is directly proportional to the frequency via a proportionality constant called Planck's constant, which has a value of 6.63 by 10 to the minus 34 joules per second. In 1905, Albert Einstein was able to use this relationship to explain the photoelectric effect, which until then had escaped a satisfactory explanation by the prevailing classical physics at the time. The photoelectric effect involves shining light or electromagnetic radiation onto a surface with the result being a release or emission of electrons. At the time, light was considered to be a wave. It could be reflected, refracted, diffracted, and it could set up interference patterns. All of these are properties of waves. Einstein's intuitive leap, which won him the Nobel Prize some years later, was to consider light to have particle-like properties, as well as having wave-like properties. It turns out that in some instances, like the occurrence of the photoelectric effect, the explanation is best derived using a particle description of light, acting as tiny little packets of energy, and the energy of these particles can be transferred to other objects or systems, such as electrons, to increase their energy. In the case of the photoelectric effect, the energy of electrons is raised to such an extent that they are driven from the surface of the material. These little packets of energy that make up light are now known as photons. And according to the Planck-Einstein equation, long wavelengths of light, or small frequencies of light, correspond to low energy photons. And we find relatively low energy photons in red light, infrared radiation, microwave radiation, and radio waves. On the other hand, short wavelengths of light, or high frequency of light, correspond to high energy photons, and we find relatively high energy photons in blue light, UV radiation, X-rays, and gamma rays. Now, understanding the atomic emission spectra of elements such as hydrogen and helium that we saw earlier involves understanding how light, or electromagnetic radiation, interacts with atoms. Now, atoms can absorb or emit energy in a number of ways. One important way involves electrons. An atom can increase its energy by increasing the energy of its electrons. So, for example, the blue dot representing an electron sitting at one energy level, and it can easily be shown to increase its energy level going up to energy level E2. Similarly, an atom can decrease its overall energy by decreasing the energy of one or more of its electrons. So that electron at energy level E2 can go down to energy level E1, thus decreasing the overall energy of an atom. So how do electrons increase and decrease their energy? Electrons can increase in energy by absorbing photons of light. So the energy of a photon can be transferred to an electron to increase its energy, and in that process that photon is annihilated. It ceases to exist. The magnitude of the energy increase depends on the energy or the frequency of the incident photon. Conversely, electrons can decrease in energy by emitting photons. So electrons transition to a lower energy state by the emission of a photon, and the energy or frequency of the photon that is produced is a measure of the magnitude of the energy decrease. However, atomic emission spectra show that only certain discrete characteristic wavelengths or energies of light are emitted from atoms. So in other words, only certain energies of light are allowed to be emitted from atoms. It therefore follows that only certain energy levels are allowed to exist within atoms that electrons are able to occupy. And thus we come to one of the most important consequences of quantum theory, as well as one of the most important scientific discoveries of the 20th century, that the electrons in atoms and molecules exist in definite, discrete, non-continuous energy levels. The energy an electron can attain is not arbitrary, it is quantized. And the evidence lies in the observed atomic emission spectra of atoms and in other observed phenomena, such as the photoelectric effect, the Compton effect, and blackbody radiation. If we want to draw an analogy with the electron energies in atoms, we can use a ladder as an example. A person can climb up and down a ladder, raising and lowering their energy, only by going from one rung to another. That person is allowed to step from any rung to any other rung, but cannot stand in the gap between the rungs. Similarly, an electron can jump from any allowed energy level to any other allowed energy level, but it cannot exist in the gap between energy levels. To move from one energy level to another, an electron must gain or lose just the right amount of energy. Unlike the rungs of a ladder, however, the energy levels of an atom are not equally spaced. In fact, the energy levels get closer together the greater the distance from the nucleus. So let's have a look at some characteristics of electrons in atoms. Electrons exist within atoms in discrete energy levels and cannot gain or lose an arbitrary amount of energy. They can only move between specific allowed energy levels if the exact amount of energy is supplied to or lost by the electron. In loose terms, electrons close to the nucleus have low energy and electrons well away from the nucleus have high energy. It's possible for these electrons to move between the discrete energy levels if the levels are not already fully occupied. Electrons move to a higher energy level by absorbing energy, typically from photons, and they move to a lower energy by emitting energy, again emitting photons. The energy gaps are fixed within a particular type of atom, but they differ between different types of atoms, and so the emission spectra for different atoms are therefore different, with emissions at different wavelengths corresponding to different energy gaps in the electronic structure of the different atoms. So what we have here is a representation of the allowed or available energy levels for the electron in a hydrogen atom. Now remember, the hydrogen atom has only one electron. Its atomic number Z is equal to 1. And because it only contains a single electron, the energy level diagram for hydrogen is simple compared to multi-electron atoms, which we will consider in subsequent videos in this series. The allowed energy levels are labelled n equals 1, n equals 2, 3, 4, 5, 6, etc. up to n equals infinity. And as you can see, the energy levels get closer together as n increases. Now if we heat a gaseous sample of hydrogen, we can increase the energy of the electron in the hydrogen atoms to one of these higher energy levels. And these are called absorption transitions. Electrons are transitioning from one energy level to another by the absorption of energy. It should be noted that if we provided enough energy beyond the n equals infinity energy level, then the electron will be lost from the hydrogen atom and we will form the H+ ion. But for now, let's just limit ourselves to the case where the energy provided is sufficient to raise the energy of the electron, but not so much as to undergo ionization. Electrons at higher energy levels will only stay in that excited state for a very short period of time, and there's a very strong tendency to transition back down to lower energy levels, thus losing the excess energy. These transitions are called emission transitions, and electrons are transitioning from one energy level to another by emitting energy in the form of photons. And in this case, where electrons return to the lowest energy level, the n equals 1 energy level, the energy decrease is relatively large, and it corresponds to the emission of ultraviolet radiation. Now these transitions are not visible to the human eye, but they can be detected by UV detectors. For electron transitions down to the n equals 2 level, the decrease in energy is significantly less, and these transitions correspond to photon emissions in the visible part of the spectrum, where we see the characteristic red, blue-green, indigo and violet emissions that we saw earlier in the emission spectra for hydrogen. For electron transitions down to the n equals 3 level, the decrease in energy is even smaller, corresponding to photon emissions in the infrared region. Again, we can't see these emissions with the human eye, but they can be detected using infrared detectors. A question that's often asked about this diagram is, why are there so many possible transitions occurring simultaneously when there is only one electron in a hydrogen atom? And the answer is that any sample of hydrogen atoms contains trillions of atoms, and across all of these atoms, all of these transitions are occurring. So the net effect is that a sample of gas will show all of these spectral emissions simultaneously. So there you have it. The only explanation for the atomic emission spectra that we observe when we heat gases is that the energy of electrons is quantized. Electrons in atoms are restricted to certain energy levels, and this has significant implications for the chemical properties of atoms, including how they bond with other atoms.